Hi everybody, welcome back. So we've calculated our total circuit impedance. I've gave us some parameters of 120 volts at 60 hertz. So what we're going to do now is we're going to calculate the total circuit current of what we have presented using the proper magnitude and the proper angles. We're going to keep that consistent through this whole method using that polar method, those values, so we continue on with that accuracy. All right, so if I'm trying to determine what my total circuit is, so total circuit current, we know from Ohm's law, I'm going to take my applied EMF, divide it by my circuit impedance. And keeping with the polar method, I actually want to make sure that I have those vectors because I want a current and know where it is with respect to time. So I need my voltage at its angle, my impedance at its angle, and that's going to determine what my total circuit current is at its appropriate angle. So with my EMF, I have 120 volts at 0 degrees because it is my established reference. It's the thing that remains constant. And I'm going to divide that by my impedance, which is 15.62 ohms at 39.8 degrees. So when I compute this, I get a value of 7.68 amps at negative 39.8 degrees, which is perfect. And you'll notice the angles are the same, and they should be because that's the only thing that's present. I'm doing 0 divided by that 39.8, and with the polar form, that's going to tell it to lag by that angle, and this makes completely logical sense. I have an inductive circuit, an RL, so resistive and inductive circuit. Within that circuit, I should have a lagging current. So I have a current that's lagging its reference by 39.8 degrees, which is perfect. That's exactly what should take place. So what I really appreciate about this method is the simplicity of it. We've removed a lot of steps. Okay, we're using the appropriate voltage at its reference. We're keeping the angles intact. We're using all of the values that we have present. It's going to increase our accuracy. We've reduced the number of steps, and that's going to allow us to make fewer mistakes. I know for myself, the more steps in an equation, I can race. I feel like I'm pressed for time, or I'm just having an off day and I clip through. The more steps, I am more prone to making mistakes. So when I evaluate this, I want to decrease the number of steps that are present. So some things I will do is, rather than doing this in 2 steps like this, I will take 120 volts and divide this by how I computed this right from the get-go, just to reduce that. And I've turned this into a 1-step problem. But just to show the breakdown of the steps, or the process to go through and how this circuit works, is really good to understand. So I have 7.68 amps at a lagging current of 39.8 degrees. So if I were to draw that on a Cartesian plane, I would have voltage at 0 degrees, lagging would be, or negative 39.8, lagging by that 39.8 degrees would be my current vector. So I hope this has helped, and I hope we get to see how we're simplifying this by using the tools that we have available to us. I hope this has helped, and we'll see you in the next one.